Okay. Can continue, Sunai. Thank you.
Okay. I'll start with it. So yesterday we made some inverter and which can drive an higher load. Okay. So it was about designing an system with higher current ratios. Okay. So today we will start with timing issues, but by the end of today's session, we would be again practicing inverters only. And today I will ask you to design an inverter of various categories and shape and sizes and tweak around the inverter. And probably then I will ask you to design a couple of gates, okay? Based on fingers, that is NAND and NOR. These are two basic gates we all have. So we will make these two gates and start with it and cover some concepts in an interesting manner if I try to do that. Okay, so we start with the PPT first. Okay, Aradhya sir, can you allow me to share my screen? I believe you have to make me as co-host. Aradhya sir, come in. Aradhya sir. Hello, Aradhya sir, come in. Okay, I just making my call. Okay, my sharing is disabled. That's okay. It'll just take a minute to do this. Okay, the phone is ringing. You can hear.
Hello.
Sir, can you make me co-host?
Yeah, I made it, you know.
I think so. Not.
Is it okay?
I just try again now.
Yeah.
Yes, this is okay now. Okay. So today we move forward with timing issues. Anyone, if you have some serious doubts, then we can talk about power back again. Otherwise, we move to timing part. Okay. So timing analysis is a part of the entire design flow where you get to know about how your circuit is going to behave or perform as per the timing requirements. Okay. Because what happens many of the time the design are functionally all okay, but they okay. And most of the time, what happens? The timing errors or issues are not what went wrong. Knowing what was wrong at what point of the system. Okay, so they are very different than normal fault analysis or other type of stuff. So timing classifications, it's all about the type of circuit you design with the digital circuit or maybe analog. So generally in digital circuit, these are the three classified types of configuration. One is synchronous. I believe everyone is familiar with the synchronous asynchronous system, and because I believe you must have gone through the digital logic circuit subject. And synchronous system is a set of circuit or a group of circuit or digital circuits. They work commonly with one global clock. Okay, so that means everyone propagates the data on the same clock signal. Okay, so it's just like a group of military soldiers. They are march past. They are doing a march past on the same clock. Okay, so everyone is synchronized. The data propagates nicely, and everything is cool and smooth in case of synchronous system. Okay, so now what is asynchronous system? Okay, so these are like self-controlled system where they do not depend on the clock. But remember, they have clock because the clock is required to operate the circuit. But for data propagation, they do not depend on the common clock signal. The data propagation happens on the handshaking. Okay. So before understanding asynchronous, let's understand the synchronous back again. So synchronous is like there are a set of there is a stage of 10 jobs. For example, assembly of some maybe a box. Okay, so there is first labor who takes the material. He takes 1 second. The second labor, he just take all the materials and assemble them in a box. So he takes 5 seconds. Then he propagates the box to the next guy. Okay, so the third guy, he just puts some paper on the box. So he takes 3 seconds. Okay. Then the fourth guy, he just puts the material inside the box. So he takes only 1 second because putting the material inside the box is very fast. Okay. Then he give the box to the next guy. The last guy just put the address label and he just ships it. He takes 2 seconds maybe. So what is happening that there are different stages of the design or the packaging of the material. Okay. So some guy takes 1 second, some guy five, sometimes some guy takes 2 seconds, some guy takes 1 second. Okay. So there would be only one clock signal. If you want to design a synchronous system, so what will happen that everyone will move on a same reference clock. Now, can you tell me that if this is a stage design, okay, if this is a stage design, then what should be the clock speed? Are you clear with the question? Okay, I'll just share it again. Okay, so you have the first stage. Okay, so you just take the material. Okay, so this guy takes only maybe let's say 2 seconds. He gives the material to the next guy. He makes a box. He takes 5 seconds as the second stage. Okay, he gives it to third guy, and in 2 seconds he puts the paper on the box. Okay, he gives it to the fourth guy. Okay, and he places let's say label on it, and again he takes only 1 second on the label, and the material is dispatched. Let's say this was an the server of the or the maybe the dispatch room of the Amazon delivery service. Okay, so this is how people work. So the first guy takes 2 seconds, second guy takes 5 seconds, third guy takes 2 seconds, fourth guy takes only 1 second to do his job. Okay, so let's say if this was everything was kept on a conveyor belt. Okay, so there was a box and the conveyor belt, I mean, like it has to move. The conveyor belt has to move. So at what speed every stage should move? Okay, at what speed? Can I have some answers? Should it move at 1 second every second that the table shifts? Okay, like you must have seen the conveyor belt automized industrial system. It should move at 2 seconds, it should move at 4 seconds, it should move at 5, or it should move at 2 plus 5, 7, 7 plus 2, 9, and plus 1, 10. So what should be the speed? 1, 2, 4, 5, 10. Can I have some answers? Okay, I get one answer at least. 5, 5, 10, 5, 10, 5, 5, 10. Why not 2? Because the 2 is the majority of people are working at 2. Why not 2? The other one guy is too slow. This guy maybe is a lazy guy. This guy is the most lazy. And this guy is being a hero, huh? He's not doing too much of work. Isn't it? So why not 2? Because they are, the majority of people. There's no democracy. Huh? Isn't it? We are working in a democratic country and environment, so why not 2 seconds? Okay, so still you guys are insisting on 5 seconds. Okay. Yes, 5 seconds is the right answer, because if this guy who's working at 2 seconds, okay, he does his job and fetches to the next stage. So what will happen? This guy is able to complete at 5 seconds only. So he will be never be able to complete his job, because what is happening? His desk would be cluttered. Okay, his desk would be full of stash and other material, because he's not complete. He takes 5 seconds to complete the job. So at least he should be given 5 seconds to do the job and complete the job. So it's just like synchronous system. This is synchronous system. Everyone will work at the speed of 5 seconds. Okay. So this is about democracy. This is about actually synchronous system. Everyone will move with the speed of the slowest guy. Okay. Everyone moves with the speed of slowest guy. This, you remember this. Okay. Slowest guy. So, but then designing synchronous system are easy, no complicacy, no hassles, no glitch. Everything runs very smooth. Okay. So the other way is that you design a synchronous system which works on the handshaking. Okay. In which what happens, if I have done the job, I ask the next stage guy that, boss, I have done my job. Do you want my data and would you like to process it? And if he's available, if he's free and he can process it, okay, so he will give me an acknowledgement signal. Then I will pass on the data and he will start processing and I can move ahead with the taking any of the new data. So that is a single system. But designing a single system is quite complex, very complex. Okay. And most of the designers, they don't prefer to use Anchor system because timing analysis, everything is very difficult for asynchronous. Whereas hybrid system enjoys the benefits of both. So wherever there is a common logic processing, they use a synchronous system logic, and wherever there's a peripheral interface, they use asynchronous logic to propagate the data. So they try to make the system a little higher performing. Okay, but again, that is very complex. So most of the designs are based on a synchronous design because they're simple, easy to analyze, and easy to design and implement. Because otherwise, implementation time is very high. Okay, so these days clocking is also a big issue because you have millions and millions of transistors and millions and millions of flip-flops who works on the clock. Okay, so you have to ensure that your clock reaches to each and every corner of the chip. Okay, so distributing the clock signal is very important because you need to have the same delay of the clock from its input pin to each and every flip-flop clock pin. So doing that is very complicated because the clock network has to reach at each and every corner and geometry of the chip. So that's why there are various techniques which have been designed and practiced by the designers who try to make the clock delays as low as possible or at least as equivalent as possible. Okay. So that's why they make use of clock distribution like H-type tree. H is like simple, like this. For example, like you have some chip, some circuit over here, some circuit over here, some circuit over here, some circuit over here. Okay. Now, what if I do like this? I just end, man, this is my chip periphery. For example, this is my chip periphery. Okay. If my clock enter from this corner of the geometry, and then I just give it to this guy, then I give it to this guy, then probably I just take it over here and I give it to this guy, and from here I give it to this guy. So what is happening? So probably my delays will not be equivalent. From here, from chip pin to this guy, it will reach fastest. To this guy, it will be the second fastest. To this guy, it will be third fastest. Okay, and this guy, it may be, I think, maybe second or third fastest. Okay, so the delays will not be consistent. So the user will not enjoy the equivalent delays. Okay, so if he designs something like H-type tree, sorry, some glitch in my drawing. If I design an H-type tree, if there is one part of logic here, one part is over here, and one part is here. So what is happening? My clock comes to the central location of the chip, and then I distribute to different zones of my chip. So this will have equivalent delays. Okay. So even the task of the designers is to handle, sorry, what's happening? Handling skews and jitters. Okay. So handling skew and jitter is a very complex issue. Okay. And complex comes later. First, let me ask and confirm that, are you guys familiar with skew and jitter? Are you guys familiar with what is skew? And what is jitter? Maybe a couple of yes, no will make me understand. Okay. In the group, there is always one or two guys who always say yes to everything. Okay. So, okay, no problem. I just cover it. Mhm. Okay. So you must have seen something like this diagram, the D-type flip-flop, right? Okay, so that's a D-type flip-flop which is having a clock. Okay. Okay, so that's my clock signal. Okay, and there is another flip-flop who takes the input from the first stage flip-flop. This is my first stage flip-flop. This is my second stage flip-flop. Is this okay? Visible? Okay. So now let's say due to some reasons I placed a buffer in between this clock node. Okay, I placed a buffer. We just uh, put some power or current to the clock load and make sure that the signal will be driven properly. Okay. Now what happens that I apply a clock over here. I give a clock signal on this point at this point. Okay. So over here, the same clock signal, okay, do not reaches the same time. Ideally, it should be here, but actually it reaches by this point in time. Okay. So you see this much delay is there. Okay. So why that delay is there? Because there was a buffer in between. Okay. So he's delaying anything which is coming to its input and giving to the next stage guy. Okay. So the same clock edge, remember the same clock reaches to the next stage flip-flop in a delayed format. The same clock edge, it's the same clock edge which reaches the next flip-flop in delayed format. And the delay is positive delay. Delay is positive delay. So this is called as Q. So this phenomenon is called as clock skew. Okay, so this is called as clock skew. So clock skew is nothing in by definition. Uh, you can say that it's a difference in time for the arrival of same clock at two different registers. Okay, or two registers means flip-flops. Okay, so that's in clock skew. The skew can be positive and negative. Okay, so this is positive skew because it is helpful to some extent. We will talk about that later, how it is helpful. The second flavor of the skew comes in vanilla. Okay, and here it goes. Now let's say your clock is coming from the right hand side of the chip. So this guy gets the clock first. This guy gets the second one. You saw this? The data is coming from here. Okay, the data is coming from the left side of the chip. Okay, and but the clock is coming from the right. So what is happening now? This guy is getting the clock first, and the second flip-flop, the first flip-flop gets the clock in a delayed format. So this is actually a negative skew. Okay, and not that helpful. Okay, it can be dangerous to some extent. So this is about skew jitter रहेगा, jitter रहेगा. अरे ड्रॉ कर गया. Okay. So it is clock period is not repetitive. The clock period is not repetitive. Okay, so that is nothing but called as jitter. So for example, you give a clock and the clock is like this. Next time, the next cycle, it might have a little more rise time, it may have less rise time, something like this. So let's say the period was 10 nanoseconds and this is 10.1 nanoseconds, or maybe 10.05 nanoseconds, something maybe small value. So clock cycle to clock cycle, one clock period is of 10, another clock period is of 10.1, maybe third one is 9.9. Okay, so from clock cycle to clock cycle, your clock period is changing, and the period may be, I mean, the on period may be different or the off period may be different, anything. So when you don't have the same consistent performance of the clock, then this is called as clock jitter. Okay, and why both of them occur is interesting to know and learn about, and how to sort is another level of interest. Okay, so clock skew happens because of the buffers in between. The skew happens because of buffers and the path delay. I'm so sorry about this whiteboard. I should use whiteboard. Is it whiteboard visible?
No, sir.
No?
Oh, sir.
Okay, now I think it must be visible now. Whiteboard. So the skew is because of buffers. Okay, amplifiers or buffers are same thing, or the path delay. So because of this, the skew happens. Okay, whereas jitter is what cycle to cycle clock delay. I mean, from one clock period to next clock period, the delays are not exactly the same. They are different. Okay, so they are due to your, you know, variation in power supply, variation in voltage, current applied to it, or fabrication parameters. All these, based on these values, your jitter would be different. Okay, so that's why controlling jitter can be quite complicated if the jitter is very high. Okay, so generally there are two branches of timing analysis. One is called as static timing analysis, or the STA, commonly known as, and another one is DTA, that's dynamic timing analysis. Okay, and in most of the companies, you have separate teams exclusive for only for timing analysis. So there's a lot of expertise between the people who are a little more experienced in handling the design, and they help you to not only find the maximum operating frequency. So STA is a technique by which you can find the maximum operating frequency of the digital circuit or the RTO circuit. Okay, and it do not apply any external inputs. And STA is analyzing all the design path, I mean the timing paths of the design, and it will keep on optimizing the design till it meets the timing constraint, or maybe put a failure tag on your design and give you an alert. Okay, so has any one of you, or are you guys familiar with ST issues, the timing analysis, how you find out what is the maximum operating frequency of the circuit? Okay, no problem. We cover it. There's no issues to this. Okay. Let me share this.
Vinayji, after this module, just tell me so that I'll disconnect it and then connect it once again, the recording, so that it will split into the modules.
Yeah, sure, sir.
Okay.
I'll do that. Okay. So let's find out what is the maximum operating frequency of a circuit. Okay, and how does the STA finds out? So STA is like, let's say you have some design like this. Okay. Don't look at the functionality of the design. It's just like, mera mood aaya to maine aisa banaya. Okay, so let's say some circuit is like this. Okay, and the delays of each gates are mentioned over here. This is 2, this is maybe 3, this is 1, and this is again 2. So these are the delays of the circuit. Okay. Okay, so how much is the delay between A to B? Sorry, not A to Y. How much is the delay between A to Y? You can type the answers. A to Y. How much is the delay? Okay, so it is like that you have some signal which will pass through all these gates and come to Y. So how much time will it take? It will take 2. Okay, it will take 2 plus 3 plus 1 plus 2. Just give me a total. So that is 8. So 8 time unit is the delay. Okay. Now what is the delay between B to Y? Same, 8. Now what is the delay between C to Y? Okay. So it is 6. Same logic, D to Y, it's 2. Okay. Great. Now you are familiar with the delays that one path is of 8, one path of another is 8, this is another 6, another 2. Now we have seen the synchronous system that everyone should move with the same speed, even though there is some guy who's fastest among us. It's just like, moving with the, with the herd. When everyone moves together, you have to move with the speed of the slowest guy. Okay. So at what speed I should apply the input? If I ask you this question, that at what speed I should apply the input? Is it 2, 6, or 8? Can I have quick answers? 2, 6, 8. Sorry, no, you don't want an answer, or like sorry for what? Yes, 8. Because if you apply at the speed of 2, so you can't expect the change because your A, B, C, D, they are together a 4-bit bus, isn't it? This might be an important block in your arithmetic logic unit, and he's computing something. And this is a 4-bit bus, A, B, C, D. Okay. So you given values like this 0, 0, 0, 1, 0, 1, 1, 0, something like 1, 0, 0, 1, something like this you give it. Okay. So uh, if you apply at the speed of 2, then probably you will not have the same input, I mean, the combined output, because for any change at A and B, the system will take 8 seconds or 8 time units to respond. Okay. So you have to move at the speed of the slowest guy. So that's how the signal system works. Okay. So this is it. So this is a common logical processing of the timing paths. Okay. So these are called as timing paths. What you just saw just now, A to Y, B to Y, C to Y, D to Y, these are all called as timing paths. All these are called as timing paths. And what STA does, static timing analysis, he finds out all the timing paths and their corresponding delays. And to do this, did I apply any logical input? Did I apply 0 to the system? No. Did I apply 1 to the logical system? System? No, nothing. Did I apply any kind of input to it? No, nothing. I have to just know manually that, okay, this is the delay between these two nodes by knowing the delay of each and every blocks in the design. And that information I will get from the library. The technology library file I'm using, from there I will get this information. So that's why it is called static timing analysis. So he lets you know the delays of each path, and based on this information, you can decide at what frequency you wish to operate. Okay, so remember this. Okay, and about DTA, DTA is about simulation. Okay, so DTA is like he just verifies what STA is talking about. Okay, for example, I'm not sure about your city geography and the maps, but for example, in your city, and you are at, let's say, this any place in the Bangalore, and I ask you to reach to railway station. Okay, so based on the map, you can say that okay, this is around 10 kilometers, and moving at the speed of 40 kilometers per hour, I may take maybe 40 minutes to reach over there. Okay, 40 or 50 minutes to reach over there, isn't it? So that's very simple. So the question is, did you really travel to that path? No. It's just like when you ask Google that I'm sitting at this location and tell me how much time I will take to reach to the railway station. So did Google goes to the railway station and gives you the answer? No. He just makes a basic calculation that okay, you are this much distance away from the station or the destination, and what is the distance, and what is the hour of the day, the traffic issues, and based on that factors, he just give you an estimate. He's not giving the actual figure. He's just giving an estimate that this is what time it will take to reach the destination. Okay. So once you have that one, so that job is done by the STA. This is nothing but the STA. So he gets you the figures that ठीक है भैया आपकी maximum speed इस circuit के अंदर ये हो सकती है, इससे ज़्यादा नहीं हो सकती. So then you verify that using an DTA. Okay. So you do the dynamic timing analysis. Okay, where you actually run the system at that speed. So you will run the system at that 8 nanoseconds. You will apply all the inputs and you will see that are all these inputs giving me the correct result at that given speed. Simple. So that is nothing but DTA. Okay. Okay, so I believe you must have seen many products in your life where everyone is labeled with some figures like that. This works at 2.1 gigahertz, or something works at 2.4 gigahertz. Okay, or any of the design is working at 1.2 gigahertz. Okay, so generally, which is this timing path based on which the calculations are being done? Okay, so let's talk about that. So from where these figures come. So generally this figure comes from the maximum operating frequency of the circuit. That comes from this type of timing path, which is called resistor to resistor delay. Okay, this is called as resistor to resistor delay, or from one flip-flop to next stage flip-flop. So this delay is taken care of. Okay, so in this what happens that the timing period is what like this is the delay of this flip-flop. Okay, because when you apply a clock edge, what will happen? You apply a clock to the first flip-flop. So whatever is present at the D input, that will be transferred to the output. But this can only happen, the D to Q travel will only happen when there is a clock. It's just like, I mean, like for the 100-meter races, there's a referee who fires a pistol, then only everyone starts running. Okay. So from that pistol, the timing is, the timer starts. Okay. That from that pistol, the timing measurements are done. It is not from when the runners start running. No, it's not from that point. Okay. So this delay is called as clock to Q delay. Okay. That's why it is called clock to Q delay. Okay. Then the data passes in the AND gate, inverter, or any multiplier divider. It can be anything, any damn thing. Okay. So this is called as propagation delay of the logic. Okay. Then you just add a setup time of the next stage flip-flop. Okay. There is some factor or the time factor of the flip-flop, which is called setup time. So if you add all these three figures, you can have your minimum clock period at which your circuit will work. Okay. So um, Anyone familiar with setup and hold times? Because I talked about setup time. As usual, as I said, there are a couple of people in the group who say yes, the rest of the people say no. Okay, so how many of you are familiar with setup time and hold times? And the other question is that why I asked in this slide also that why only this path is taken care of. Gee, getting lots of no's. It's okay. Okay. I got it. No problem. We just cover the setup time too. Are you guys familiar with the construction of the flip-flop? Just asking for my knowledge purpose, so that I need to keep a bottom hand that from where I have to start. I mean, the flip-flop construction you're familiar with? Then you should be familiar with setup time, no? Okay. This is enough. Yes. If I get more than 5-6 yes, I will say I will take the yes. Otherwise, no. Okay. Okay. I just use the board. So you must be familiar with flip-flop construction, D flip-flop construction like this. Yes? Okay. Now tell me one thing. Does any digital circuit has a memory element? This is what? This is called a 1-bit memory, right? This is basically you call it a 1-bit memory. क्या सच में मेमोरी नाम की कोई चीज होती है डिजिटल सर्किट्स में? सिर्फ DRAM, probably DRAM. Okay, but जनरली क्या एक फ्लिप फ्लॉप एक मेमोरी सच में है? Yes or no? क्या फ्लिप फ्लॉप सच में एक मेमोरी है? I mean, ये मतलब अध्ययन वाला क्वेश्चन हो गया. This goes too much philosophical. Okay, don't mind that. Actually, no. Okay, try to understand. It's a temporary memory. Yes, it's a temporary memory. If you turn off the power, the things are lost. I wish the humans can also have the same functions, that you wake up in the morning and all the bad things are washed off. Okay, so actually this is how this flip-flop is made up, isn't it? Have you seen this figure? I was asking about this one. Have you seen this figure? Can you give me a yes or no quick? Yeah, clock controlled memory. Yeah. Have you seen this figure? Okay, so this is what a flip-flop looks like from inside. This is, I will not say this is exactly a flip-flop, but yes, it's a latch memory. Okay, and basic SRAM cell, this is how it looks like. So how it works, that this is your data port, this is your data, okay, and this is your clock, okay, and this is, let's say this is active low. So this is your clock, okay. So what happens, that when clock is low and high, so let's say when the clock is low, what will happen? This guy is closed. This guy is closed and this guy is open. Okay. So can data go inside? No, data cannot go inside. So what is happening? So if there was a 0 here, this gets 1 here. So 1 comes here and 0 back again. So you are looping around the same data forever. forever and ever and ever. It's just like you're repeating to yourself every day. मैं बहुत अच्छा आदमी हूँ, मैं बहुत अच्छा आदमी हूँ. I'm very good. I'm very good. I'm very good. I'm very good. So this is how it is. Okay. So you are just repeating yourself. You're keeping the data and just looping around. Okay. So actually, they are just two inverters. There's no such as memory. Okay. There's nothing as memory. But yes, two inverters joined together in such a configuration that they can remember something forever. Okay. So yeah. Okay. This is how it is. Okay. It should not be. I'm sorry. No, I got stuck. Okay. So now what happens when the clock reaches to 1? When the clock goes 1, okay, so what will happen? So this will happen. Okay. So this guy will get closed. This switch, there is a switch over here. There's a switch over here. This guy gets closed and this guy gets opened. So what is happening now? What is happening now? And remember the Q is here. Huh? This point is Q. This is your Q probably. This is your point Q. Okay. This is your point Q. So let's say if the D is 0 here. Alright, so you get a 0 here, you get a 1 here, 1 here, 0 back again here. So what is happening? You were trying to store 0 in the memory. You were trying to store 0 in the memory. So this guy is taking 0, inverting it and keeping it here. He's keeping it here. He's not storing it yet. Okay, so you are getting the Q as 0. So whatever you will give a D, it'll get to the output. But now what is happening? This is at this point of time, the latch is open, the memory is open. He's trying to record, I am good, I am good. You're just programming, you're trying to hypnotize the person. Okay. So now again, the clock goes to 0. So at that time, what happens again? This guy gets closed, this switch gets closed, and this guy gets open. So what is happening now? This new 0 over here, this 0 over here is looping forever. Okay. So you wanted to store 0 in the memory, and yes, you did that. Okay. So that's how it is. So simply, you have a memory cell like this. Okay. So this was your D, and let's say this is your clock. Okay, this is your clock ports. This is active low and this is active high. Okay, and this time let's say you want to store a logical 1. Okay, and this is how the clock you give. Sorry, this is how the clock you give. So when the clock is 0, so what is happening? So this switch is closed. Okay, now you give a 1. Okay, so at 1, what will happen? This guy opens. This switch is open now. Okay, this switch is open now and this is closed. So you are actually looping the logic here and storing it. So if this was 1, so this is 1, this is 0, 0 here, and you get back 1 here. Okay, and remember this is your output actually, this is your Q. Okay, now what is happening? As you give clock back to 1, so whatever the last value is there, 1, okay, that would be, trapped inside the flip-flop or the latch memory. So this gets closed. So this gets closed and this gets open. Simple as that. And this is looped forever. Is this okay? Anyone has a question or doubts? Now, how they do it on the edge? This is about latch. This is a latch. This is not a flip-flop. This is a latch. So, for flip-flop, you just put one more guy on a stage. Sorry. But this time, reverse. This time you reverse it. This is 0, control, and this is active high. Yeah. So that's a flip-flop. There's a 2-stage latches. Okay. That will make a flip-flop. Only the clock signals are of the opposite polarity. Okay. So this is how it works. Any questions if you have? Any questions you have? Anyone? So you saw that there is nothing realistically a memory. It's just a couple of inverters and switches, and with the right connections, you can make use of this inverters to store something forever. Okay, the real memories are kind of, maybe you can say a DRAM, maybe, or FRAM. Magnetic RAMs, because once you charge the device, they will keep that information stored in them forever. Okay, like a magnet, right? So you make the magnet remember that they are always north or south pole. They will never forget that, or you can't reverse it. Can't even reverse it for that case. Any questions or doubts in this? I assume that no. Then let me ask the question. कि ठीक है, ये बात समझ में आ गई कि फ्लिप फ्लॉप ऐसा दिखता है, बट हमने शुरुआत करी थी कि सेटअप टाइम क्या है, तो ये सब कहाँ से आ गया? तो ठीक है, अब आते हैं सेटअप टाइम पे, because I wanted to ensure that you guys understand the switching and the locking mechanism of the flip-flop correctly, because otherwise it becomes complicated later part. Okay, so if this is the construction of an flip-flop, can anyone explain me what is setup time and hold time? You can come on the voice, you can unmute yourself, and someone wants to put some comment on it. So you're most welcome. You can write your comments, and writing is quite tedious process. So you can reply verbally if you want. Anyone can talk about setup time and the hold time. The time taken by whom? Before the party or the marriage, the time taken by the people to get ready and dress, that is called setup time. No. All right. You can speak verbally, I mean any one of you, because that will be more fast and easier. Am I audible loud and enough, clearly? I hope today I'm not using any headphones for my mic. So I believe, yeah, my speaker is also okay. Minimum time before the clock activates. Yeah, that's a good one. Minimum time, I'm gonna hold the clock in logic 1. Okay. Okay. That's good. So you guys are really good here. Like, okay, keep going. If anyone else wants to comment till the time I just draw it back in a neat format. Okay, so I'm getting very good answer. Okay, so making use of Google. That's nice, huh? Jai Ho Google Data. Okay, that's okay. Okay. Till the time you understand it quite well, there is no issues in getting the answer from any source. Okay. So this is what the construction of FF looks like. At least we are clear on this, and we are establishing this fact very well, that there is nothing time-wise. Because these are just switches and inverters. Did you heard anything about inverters having any time requirement, that inverters require setup time, or the inverter requires hold time, or at least you should pump the inverter before using it for a few minutes, then only you can make use of it? Or if you're applying a clock signal to the inverter, then you should not apply faster than this or slower than that. No, nothing like that. There's no such thing with inverters. Then why all of a sudden, when you configure them in a memory element, then why all of a sudden the setup time and hold time comes to in the picture? Okay, it's like this. Okay, the question becomes evident. Okay, so what and how it is. Okay, so to try to understand in very simple manner, I believe every one of you must have used the glass doors, the automatic glass doors, at some restaurant, or maybe some banks, or at some shopping malls, or in the offices. You must have seen some, fancy glass doors that you come and stand in front of it, and they slide open for you. Just you pass through, and slowly they come close. I believe everyone must have seen it. Yes, right?
Yes, sir.
Okay. So imagine there is you go to a mall, okay, and at the entry of the mall there is such a beautiful glass door is there, and from far, you were watching some people passing through that glass door, and the people were just coming to the glass door and walking through it. Okay, now will you try to do this, that you become so excited that you start running towards that door and you don't stop? Okay, you try to run and try to pass through the door. How many of you have done this? Anyone has done this? You can raise your hand or maybe say yes or no. If anyone has done it, then only say yes. That yes sir, मैंने एक बार ऐसा किया था. Sabash, you have done this? Very good. What happened? Did the door open? You have to run at the fastest speed possible of yours. It's just like you are running a 100-meter race. You're putting your entire energy into it, and you rush towards the door, and you expect the door will open. Security staff, okay. So security guard must be a really good sportsman, because someone who's running so fast and rushing towards the door, he must be really quick. Reflexes he must be having it anyhow, but I'm sure no one would do that, right? It stayed open. No, while it was closed. When it was closed, you are running towards it, okay, and run and try to get inside the door. Probably the higher chances are that you will definitely bang the door, and you might injure yourself, or you may break the glass, or something wrong will happen for sure, isn't it? So you don't expect that door opens such a fast manner that you can pass through running. Okay, so you allow him to open, give some time to open and close. So the same is with the data. Okay, so what happens then when you apply a clock to the fifth law? So this is the active edge. Let's say the positive edge is the active edge of the fifth law. So what happens at this edge? What is happening at this edge? What is happening at this edge? He is opening and closing the doors and the switches. The doors in this flip flop are the switches. So he's opening the doors, taking the data inside, and closing back the door again. Okay, so this is all an entire process. Okay, so in this case, this must be closed at the first stage, and this is closed at the first stage, and this is open on the first stage. So what is happening here? He is looping the previous data, isn't it? And he is taking the new data, which is available over here. And this is at this low level. And as he touches the higher level, So in a single edge, what operations happen? This guy gets open, okay? This guy gets open, and where's black? Yeah. This guy gets closed, and this guy gets closed. So the new data is trapped over here instead of the second stage. Okay. So let's say you have trapped one over here. Let's say you have trapped logic one over here. So what you will get here? One. That's your queue. You will get the same stuff over here, isn't it? Again and again, forever. So this is it. So on this clock edge, what he was doing is he was opening the gates, taking the data inside, and then closing back again. So this should not happen, that the data should be stable. So the data should be stable in this window. So that is your window. So the data should be stable before the active clock edge. Okay. So this is called as setup time. So this time delay, this time is called as setup time. Okay. So this is the minimum amount of time by definition, you know, the Chatur's answer from 3 Idiots, that there's a minimum amount of time the data should be stable before the active clock edge arrives on the flip flop. Okay. So this is a minimum amount of time. Otherwise, the manufacturer says that, boss, I will not guarantee. Okay. So it's just a glass door manufacturer. The glass door manufacturer says that if you want, no one should be injured, everyone should be safe, and then everyone should stand for 2 seconds in front of the door. Then my door will open and a normal human being can pass through. At least in 2 seconds, it will open this much. So anyone can pass through. Okay. So that is at least minimum amount of time period. That is 2 seconds. But someone, you know, tries to run faster more than 1 second and tries to go inside the door, I cannot assure it. You might be in luck. The gate opens it very fast. The motor was working fine. The gears were all okay. Bearing, everything was okay. So you may pass through, but there are high chances of damage. Okay. So this is called a setup time. And at the same time, even after the clock edge, the data should be stable for a while. Although this duration is very short, but still it is present. And this is called as hold time. So this is the minimum amount of clock, the minimum amount of delay, okay, for which the data should be holded after the clock edge, active clock edge. Okay. So these are the setup and hold times. Okay. Any questions? I just wait for a few seconds if anyone has question on it. No? Okay. ठीक है, तुम नहीं पूछोगे तो मैं पूछूंगा. Anyone from Delhi? Anyone from Delhi here?
No, sir.
No problem. Nothing to worry about, okay? Because in those regions there is a very famous question which is popped very frequently. You know, क्या कर लोगे बे? अगर हम तुम्हारा होल्ड टाइम एंड सेटअप टाइम फॉलो नहीं करेंगे तो क्या कर लोगे? Will you like to ask this question? If I do not follow the setup time or hold time, क्या उखाड़ लोगे? That's nice. Only South. Okay. No problem. But I'm sure this is a good attitude to carry sometimes. That what will happen if I do not follow the setup and hold time? What damage it might bring? It will store the wrong data. It will reject the data. It will reject the data. It will store the wrong data. Nothing will be stored. It will hold the previous data, or the system will go in oscillations, or system will shut down, or clock बुरा मान जाएगी. I'm so sorry. Okay. Redundancy. Okay. So what will happen if you don't follow the setup and time, hold time restrictions? Okay. So this is called as the system may into a metastable state. The system may go into a metastability state. Okay. Now, what is that? See, it's a long story short. When the output is neither 0, neither 1, because it is expected that either the output is logical 1 or logical 0 over here. Okay. But then it's okay. You may have a wrong output or correct output, that's okay, because finally the flip-flop may either produce 0 or 1, either of it. Okay. But sometimes it is possible for a flip-flop that he can enter into a state which is called as metastable state, where the output is neither 0, neither 1. Okay. It is somewhere in between. Now, what harm it may bring? Imagine this is a CMOS circuit. This is CMOS circuit, and in a CMOS circuit, any input should not be left floating. Otherwise, it may go in oscillations because of high input impedance. And keeping a value between 0 and 1, it is as good as like going in a disastrous state. So the entire circuit may propagate the same oscillations at the output, and the entire system may shut down drastically. This happens. You must have experienced your desktop computers or laptop computers sometimes just jamming. You're working on the laptop, on the desktop, and all of a sudden you just freeze. They just freeze. Nothing happens. Nothing is moving forward. They are just stuck. So probably a laptop has gone into a metastable state, and they can recover. Generally the laptops are recovered only by a forced shutdown, right? No buttons work, nothing works, because your microprocessor was executing something at very high speed. He was running a game, or he was executing some thread at the background, and he was trying to push the speed. He was trying to push the clock as fast as possible. Now the clock was running fast, so your setup and time requirement also comes down, because they are getting narrower and narrower. So the system may fail drastically, and if it is not being managed properly, the system may go into metastable state again and again, causing failure of your product itself. Okay. I just share back my video again. Is my PPT visible? Maybe 1 or 2 yes can do. Okay, it's visible. So that's why you see. That's why this maximum operating frequency of the circuit is being taken care of. Sorry, I just cancel this. Yeah. Okay. So that's why the maximum operating frequency of the circuit is based on this RTL delay. Because this is what you have. You have a flip-flop, some combination logic delay, and another flip-flop. So you start the data from here, okay, and store it to the next stage flip-flop. So that's why it is clock to Q delay. So you just add it, clock to Q delay plus any propagation path delay in between, and the setup time of the next stage flip-flop. Setup time of this flip-flop. Okay. So because this is the second guy who's storing it. Okay. So setup time iska lagega, iska nahi lagega. I mean, you don't need setup time from the first stage guy. From the second stage guy you need it. So this equation guides you, a very basic one. This is the stage 1 equation. this helps you to identify the maximum operating frequency of your circuit. So let's have a look on a little bit of fun part using animation. So here you have the same two flip-flops with some combination delay in between with the delay of TPD. So what do? You just give a clock on the first flip-flop, okay? And these are in my setup and hold time requirement of the first flip-flop. And assuming my data D1 was stable in this period, it was stable in this period, okay? So what happens? I give a clock. So what happens? My data is launched, okay? My data is launched from the first one. So when the Q1 changes, does it happen right over here? No. The Q1 changes after the delay of clock to Q delay over here. Now I have the new Q1 over here, okay? Then what happens? From this point till over here, this is the TPD delay because there is some logic in between. So he will take time to process the signal, and after the TPD delay, he will give you the output. So that means the D2, the new data over here, the new D2, okay, would be available to me after the delay what? TCQ plus TPD. So can I sample the D2 over here? Can I store it over here? No, because I'm not meeting the setup time requirement of the next stage flip-flop. So I have to wait. I have to wait this much amount of time, which is called as the setup time. So this is the setup time. And after this delay satisfying, I can sample the next flip-flop, okay? So that's why the distance between this clock edge to first clock edge would be what? TCQ plus TPD plus T setup. So you can capture it over here. So that would be your minimum clock period and maximum clock frequency, because minimum clock period and maximum clock frequency are vice versa. I mean, inversely proportional. Okay. I believe this is quite easier to understand because of the animations. Okay. So now you know this, right? That अच्छा मेरे सिस्टम की maximum operating frequency dependent है किस पे? ये formula पे. The maximum operating frequency is dependent on this formula, that TCQ plus TPD plus T setup time. Ah, this is good. Okay. So if I ask you this question, that how you can reduce your time delay, or how you can improvise your frequency, how you can increase the speed of the circuit. So which factor you will control and how? How? You just take a small poll. Maybe you can answer verbally to save time, or maybe you can type if you feel that this is comfortable.